Okay, so this is our last chapter for the semester. Chapter 6 deals with inner products and deals with vectors and orthogonality and different relationships between vectors and about vectors. Okay, so we'll look at some different stuff we haven't talked about just yet. Most of our discussions at this point have been about matrices and the role of when we look at vectors together. So now we're going to look at some properties that apply to individual vectors, and then of course we'll tie that back in to the things we've been looking at. Okay, so chapter 6 shifts a little bit, but it still ties into a lot of the same things we've been talking about. We'll still use a lot of those same definitions, but just the 4 sections here, 6.1 through 6.4, to get us to the end of the term. Okay, so let's get underway here. Switch over to the other camera. So we're talking about in 6.1 here, we're talking about inner products, length, and orthogonality. Okay, so an inner product comes about when we start talking about multiplying vectors. Okay, and I'm putting it in quotation marks because it's not multiplication in the traditional sense, but there are some overlaps, and it comes about because we know how to add vectors. We add the components. We know how to subtract. We don't have a method for multiplication or division. We have some other things we can do with vectors, but we don't have some of those methods, and so mathematicians tend to generalize things. Okay, well, what can I do for a real number? Can I stretch that out to a vector? Okay, so we're going to look at multiplying vectors. Okay, if you think about what we can do so far, right, if I have a vector u, I have x1, x2, and that goes all the way down to xn. And I have a vector v, which we will do y1 through yn. Okay. Right now, I can't do u times v. Okay, I can't multiply those because I can't go across and down, right? I have only one entry across, but then going down, I have way too many. And the same thing for v times u, just switching the order still causes the same problem. Okay, but I do notice that if I made one of them transpose, so maybe I do u transpose v, now these both have n entries. So if I flipped u to the transpose, now it would be a row instead of a column. And so I could go across those entries while I was going down v. That I could do. And the same thing, if I made v transpose u, I could do that same multiplication process. Okay. And when I did that, if I did u transpose times v, I would get a single 1-by-1 matrix, okay, which has a product here, which I'll call A for the time being. Okay, because I would go across, which in this case would be entries 1 through n, and I would go down v, get entries 1 through n. So this product would actually be, I would do x1 times y1 and add it to x2, y2, and that would continue all the way to the end for xn, yn. Okay? So that's the idea of an inner product. Okay? So this u transpose v is called the inner product. Okay, that is a broader term that can apply to lots of different types of products, is an inner product. Some criteria we have to meet, but specifically, it's the inner product for vectors. Okay, so there's other types of inner products that we can do on real numbers, things. There's lots of inner product ideas, operations, and spaces. But specifically for the inner product for vectors, we call it the dot product. Okay, which in this case would be simply denoted u dot v. So u dot v. Okay, and that's going to equal some scalar a. That is a real number. Okay, we don't write that 1-by-1 matrix as a matrix because it's just the number. It's 1-by-1. It's just the one position. So we typically just write it with the one entry a as a real number. Okay, so inner products or dot products yield real number outputs. So I multiply these two vectors, or I dot these two vectors. Okay, so u dot v is how we read that. And the result is a real number, not another vector, not a matrix, but a real number. Okay. All right, so let's look at a couple of straightforward dot products here. So I'm going to have u, it's going to be 2, -3, 1. And v is going to be 7, 1, -1. Okay, and I'm going to find u dot v. Okay, so I'm going to do u dot v here. So I'm doing, match up the pairs. 2 times 7 plus the second one is going to be -3 times 1. The third one is going to be 1 and -1. Okay, add those together. So I've got 14 minus 3 minus 1. I get 10 for that dot product to UV. Okay. Now I could do lots of operations here. Maybe I want to do V dot itself. Okay, so I'm going to do V dot V. That's 7 times 7. That's going to be 49. Plus 1 times 1 is 1. And then minus 1 times minus 1 is a positive 1. So I add those together. V dot V is 51. Okay, maybe I want to divide a couple of dot products. So I do U dot V divided by V dot V. Well, I can take 10, I already found that, and 51 for V dot V. I already found both of those, and then I divide the results. Simple enough. Okay. I can do lots of operations here. Maybe I want to do U dot V, 1 divided by U dot V times V. Okay. So notice here U dot V is going to be a real number, but V is a vector. So U dot V I already found, it's 10. So this is going to be 1 over 10. But then V is still a vector. So the result of this multiplication is going to be that vector. Remember, we multiply scalars by vectors by multiplying the coordinates. Okay, so I've got 7/10, 1/10, and negative 1/10 because 1 over U dot V was 1/10. Then I multiplied that by the vector. Okay, so be careful. If there's not a dot there, then we're not talking about dot product. Okay, V is a vector, so this is a scalar times a vector. This is just like C times V. Okay, U dot V, remember, is going to give you a scalar output or a real number output. Okay, so let's change vectors here. New vector U is going to be 1, negative 2, and 3. And my new vector V is going to be 0, 1, and 4. So U dot V, let's do that first. I'm going to do 1 times 0 is 0. Negative 2 times 1 is a negative 2. And 3 times 4 is 12. So I add those together and I get 10 for the dot product. Let's do U dot U this time. So I'm going to have 1 times 1 is 1. Negative 2 times negative 2 is 4. 3 times 3 is 9. So I've got 14 when I add those together. Maybe this time we'll also do the square root of U dot V, U dot U. So I already found the 14, so U dot U then under the square root is the square root of 14. So you do that dot product, find the real number, and do whatever corresponding operations you are asked to do with that, okay? All right, so inner products have several properties, okay, which we will group under theorem 1. Okay, so our dot product is going to have 4 properties under theorem 1. The first property is that it's commutative. If I do U dot V and V dot U, I get the same result. Those are equal, okay? Which makes sense because the operation is built off multiplying. It doesn't matter if I do 1 times 0 or 0 times 1, I'm going to get the same result. So it's built off real number multiplication. So dot products are commutative. They are also distributive. Okay, so U dot U plus V dotted with W is the same thing as doing U dot W and then adding it to V dot W. So I just distributed that W, U dot W, V dot W, okay? It is associative for scalar multiplication. So if I have CU, C is a constant here, okay? It's a scalar, it's not a vector. Dot V, that is the same thing as doing C on the outside with U dot V inside the parentheses, which is also the same thing as doing U dotted with CV. Okay, I can multiply that scalar constant anywhere along the way that it is easiest for me. Okay, and then property 4 is that U dot U is greater than 0, greater than or equal to 0 always, okay? You think about multiplying the number by itself, I'm either doing positive times positive or negative times negative. And either way, I'm going to get positive. If I add up a bunch of positive numbers, I get a positive. So U dot U has to be greater than or equal to 0. And so I know it kind of looks like a fifth property, but U dot U is only equal to 0 if and only if U is actually the 0 vector. So remember, we're talking about vectors all through here. Okay, so only the zero vector when you do u dot u will give you 0. Other than that, it's got to be greater than, but in general, it's greater than or equal to, because we do have this case where it is 0. So those are our properties for inner products. Okay. All right. Now we could do that with more than just 3-dimensional vectors. We can do a 4-dimensional vector, 5-dimensional, whatever makes sense in our problem. Okay. All right, so on the next page, we're going to talk about length. So I said inner product length and orthogonality were our 3 things we're looking at in this section. So when we talk about the length of a vector, what we are talking about is also called the norm of a vector. Okay. And we define that using this double absolute value type notation. So those double bars on each side. So that notation is the norm of V, or also the length of V. Okay, V is a vector. Talking about its length or its norm. And then we'll define what that is for a vector. That is going to be the square root of V dot V. So we dot a vector with itself, and then we take the square root. Remember, the dot product has to be positive. So the square root, we don't have to worry about any imaginary numbers because I know what's underneath there is going to always be positive. And when I multiply, x1, remember my u's and v's back on the first page were x1 and y1. So I'm going to wind up squaring each of the components of my vector v. Okay, x1, x2, all the way down to xn. That is what v looks like. So when I take this norm, I am just squaring those pieces, x1, x2, x3, and so forth. Okay. Now the other property we should know here is if I have a scalar times that vector, I get the absolute value of the scalar times the norm. Okay. So rather than squaring them all along the way, I could just factor out that c, and it's under a square root, and the square root of something squared is itself but absolute value. Okay, so that gives us a property for norms. Okay, it's not a property of inner product, that's specifically a property of the norm, okay, which has a lot to do with an inner product because it's built off that inner product. Okay, so if I have a vector v, 2, -3, and 1, I want to find its norm. So I'm going to take the square root. 2 squared is going to be 4. 3 squared is going to be 9. And 1 squared is going to be 1. So I've got the square root of 14 for the norm of v. Okay. Now you should also notice here it's going to be useful to consider the norm squared, which is really just v dot v. It just kills off that square root. In this case, that would be a positive 14. Okay. So maybe I'm interested then in doing the norm of v, which notice is a constant, times a vector times the vector v. Okay, so the norm of v was the square root of 14, and the vector v was 2, -3, and 1. So that product would be a vector 2 square roots of 14, -3 square roots of 14, and then 1 square root of 14. So I won't write the 1 down. And there is my vector that would be that product. Okay, so the norm is also a scalar value. Okay. All right, so let's do one more here. I'm going to have a vector u. My vector u is 3, -4, and 0. So the norm of u will be equal to 3 squared, which is 9, -4 squared, which is 16, and then 0 squared, which is 0. So that's the square root of 25, which is actually a nice, easy number for us to compute. So the norm of u there is 5. Okay. Now, that should invoke an idea of the Pythagorean theorem to you. You should think about the Pythagorean theorem there, right? 3, 4, 5 triangle, okay? So you've got 3 on one side, 4 on another, and then the length along the hypotenuse side is 5. So the Pythagorean theorem plays a role here when we're talking about the length of vectors, which makes sense because the Pythagorean theorem is built on lengths in our usual Cartesian space, okay? So we need to define a couple more terms here, but one specifically. If the norm is equal to 1, we say that the vector u is a unit vector. Okay, so anything of length 1, think about the unit circle is the circle that has radius 1. So anything of length 1 is a unit vector. Okay, unit vectors are important. We say a unit vector is normalized. Okay, so a unit vector is normalized. Okay, so we have these building block vectors that are unit vectors or normal vectors. Okay, and we're interested in vectors that point the same direction. Okay, so let's think about visually. If I have a vector u, okay, and I look at all the vectors that are in the same direction, maybe they have negative, but they come out the other side. All these vectors are in the same direction. So all the vectors on that line are in the span of the vector u. Okay, I told you we would relate it back to the things we've talked about. So any constant multiple of a vector points in the same direction. Just a fancy way of saying it's a linear combination. Okay, it lies in the same line. Okay, so what we're interested in is, can I find a vector here that has length 1? Okay, can I find a normal vector, a unit vector, a normalized vector? All those mean the same thing. Can I find one of those vectors that points the same way as u? Okay. Well, I know u's length here, so I'm using this u above as my example. So u's length is 5. Well, if the length of u is 5, I simply need to divide it by 5 in order to get it to have unit length. Okay. So I can take a unit, I can get a unit vector by simply taking the vector u and dividing it by its length, which would be its norm. Okay, so a unit vector in the same direction as u I compute by taking u and dividing it by its norm, which in this case is the vector 3, -4, 0, divided by its norm 5, which is the same thing as taking 1/5 and multiplying it by that vector. So 3 divided by 5, or 3 times a fifth, is 3/5, -4 over a fifth, and then 0 divided by 5 is still 0. Okay? So to find a unit vector, I merely need to divide it by its norm. Okay? Now, you will also see questions that will talk about a basis for the span of u, for example, that is a unit vector. Okay? Well, the span of u certainly has a basis that is just u. Okay? So a unit vector that's a basis is the same thing as a unit vector in the same direction, which is the same thing as normalizing a vector u. Okay? All of those properties were found in the same way. Okay? So that would be the same answer there above it. Okay? So let's consider then a little different style of vector. Maybe I have a vector v, and this vector v is -2, 1, 0, and 2. So notice I've written it horizontally. Okay, it is still a vector if it's written horizontally like that. Okay, but it's just styled a little differently. Okay, I could write it vertically like we've been writing it. That'd be just fine. Okay, and I want to complete the same question. I want to find a unit vector in the same direction as v now. Okay, so since it's four-dimensional, that's okay. All we're doing is v divided by the norm of v. Okay, so the norm of v would be the square root. Negative 2 squared is 4. 1 squared is 1. 0 squared is 0. And 2 squared is 4. So I've got the square root of 9, which is 3. So then my unit vector is going to be negative 2 over 3. Again, I'm taking my vector that I had originally and dividing it by the norm that I just found. 1 over 3. 0 over 3 is still 0. And then 2 over 3 for the last coordinate. Okay? And I could also write that in a horizontal format. Okay, 2/3, 1/3, 0, 2/3. Okay? So this is also a basis, right, for the span of V. Any multiple of V will be a basis for it. The one we're most interested in is either V itself or perhaps the unit vector that goes in the same direction. Okay? Now we can also do this with fractions. Don't let a fraction trip you up. Okay, so our next example will have a fraction in it. Say I have a vector u. My vector u is equal to, all right, get my camera to cooperate there. Vector u is equal to 1/2, 3/4, and -1. Okay, so I need the norm of u. So the norm of u will be the square root. 1/2 squared is 1/4, plus 3/4 squared is 9/16, and -1 squared is 1. So that's all under the square root. So that's 4/16 and 9/16 is going to make 13/16. Add 1 to that, I'm going to get 29/16. Okay, use your calculator if you need to, nothing wrong with that. So simplifying that, I get the square root of 29 over 4, because the square root of 16 will be 4. So square root of 29 over 4 is the norm. So I'm going to take 1 over the square root of 29 over 4 and multiply that times my vector u, 1/2, 3/4, -1. Okay, flip that around, so it's going to be 4 over the square root of 29. Again, 1/2, 3/4, and -1. Okay, so 1/2 times 4 over the square root of 29 is 2 over the square root of 29. Okay, the 4 and the 2 simplify. 3/4 times 4 over the square root of 29. The 4's cancel, so I just get 3 square roots of 29. And then on the bottom, I've got -4 over the square root of 29. Okay, notice that middle one is not a fraction. Okay, the denominator there canceled with the 4 in the front. Okay, so fractions don't trip us up. At least they shouldn't. At least that's the hope. Okay, so length also should inspire the idea of distance. Okay, so we have the distance between vectors. Actually, I'll get a pen that cooperates here. Okay, so when we talk about length, right, that's more like the distance between the origin and a vector. Well, what about the distance between two vectors? Okay, so we're going to define the distance between two vectors the same way we would define distance on a number line. Okay, we'll also abbreviate this dist to just d, because mathematicians are lazy. So we don't like writing out 4 letters like that. So just d, and that is going to be the norm of the difference between those vectors. So the norm of u minus v. We know we can subtract vectors, okay? So we're still subtracting vectors here. So let's pick 2 vectors. U is going to be equal to 1, 3, -5. V is going to be equal to 3, -2, 0. Okay, so u minus v, again, remember to subtract vectors, we just subtract the components. So 1 minus 3 would be -2. 3 minus 2 would be 1, and -5 minus 0 would be -5. So then if I find the distance, I'm just looking for the norm. So that's the square root. 2 squared is 4, 1 squared is 1, and -5 squared is 25. So the distance between the two vectors here is the square root of 30. Okay? Square root of 30 then is the distance between those two vectors. Okay, and we could do that for any vector you like. Okay, so let's do just 2 by 2 here. So I've got 1, 2, and then my vector v here will be 3 and negative 1. So u minus v then would be 1 minus 3 would be negative 2. 2 minus a negative 1, be careful. So it's minus a negative 1, so we're really adding. So 2, negative 3. And then the distance between them would be 2 squared is 4. 3 squared is 9. So it's the square root of 13 be that distance. Okay. Now let's consider some special kinds of vectors here. So we're leading up to orthogonality was the third word there in the start of the section. So let's take a look at some vectors visually here. So I'm going to have a vector u. Okay, there's my vector u. I'm going to have a vector v. Okay, there's my vector v. Now coming out the back side would be a vector negative v. Okay, so as I look at this space here, my vector negative v is clearly a lot further away from u. So the distance between u and v would just be across here connecting those points. Okay, but from u to negative v, it's much further. Okay, so clearly the distance from u to v is not the same as the distance from u to negative v. Okay, and so why would that be important? Okay, well, let's model this here. So I'm going to put v on a map on the chart here. So here's v. Coming out the other side, I have negative v. And now I want to make the distance from u to v equal them. So I want to get now, in the second case here, I want the distance from u to v to equal the distance from u to negative v. Okay? So as I look here, if I'm going to get this distance to be the same, I better put the vector u in the middle, because I want to make these red distances the same on my picture. So as you're looking at that picture, that should invoke an idea for you. That's a right angle. Okay, so orthogonality corresponds to when this is the case. Okay, and orthogonality is just another word for a right angle or for perpendicular. Okay, so orthogonality is a right angle. Okay, so if this is the case, we say u and v are orthogonal or perpendicular. Okay, those are words that mean the same thing, orthogonal and perpendicular. At least they mean the same thing in R2. Okay, the word orthogonal is a little more broad. Perpendicular has a specific geometric context. Not all inner products have to go with geometric context. So for that reason, we say that they are orthogonal and not simply perpendicular. Okay. All right, so let's look at some relationships here, because we can actually do better than this definition. Okay, because computing the distance is not super easy, it's not super quick, but we can do better than that with some use of the definitions that we have. So I want the distance from u to v to equal the distance from u to negative v. That's what we want. Okay, well, I know from norms that it's easier to just do them squared, because then I don't have the square roots. Okay, so I'm going to square both sides, and then I don't have the square roots running around. That'll make things a little nicer for us. Okay, so I'm going to have u minus v norm squared. Okay, I'm just doing the left-hand side here first. Okay, so left-hand side. So I take that norm and it's squared. So really all I'm doing is u minus v dot u minus v. Okay, now I can apply associativity and distribution to this. So when I do that, I'm going to get u dot u minus v, and I'm going to get negative v dot u minus v. So I just did distribution. I distributed the u over to both this one and the v over to that one. Because remember, this is a vector, single vector, so I can use the dot product accordingly. Okay. Now I can do distribution on that. So I'm going to have u dot u plus u dot negative v plus negative v dot u. I didn't need that parenthesis there. There we go. Plus negative v dot negative v. Okay, well, u dot u we know is the norm of u squared. And negative v dot negative v, the negatives go together and make a positive. I get the norm of v squared. And then these two, I know this is commutative, so I'm going to get negative 2 copies of v dot u because I can switch the order of v and u. And they're both negative, so I put them together, I'm going to get negative. Okay, so I've got negative 2 v dot u. If you want to put u dot v instead of v dot u, that's fine. Remember, it's commutative. You can go in either order. Okay, so that's my left-hand side. Okay, now let's take a look at the right-hand side. See if we can make any observations here. Try to get it all visible for you here. Okay, so now on my right-hand side, get my papers to cooperate. Okay, on the right-hand side now, I have the norm of u minus negative v. Okay, so remember what the right-hand side was. It was the distance from u to negative v. But again, I'm doing squared, so I don't have to deal with that pesky square root. Okay, that just makes it easier to deal with. Okay, so really this is the same thing as saying the norm of u plus v squared, which would be the same thing as saying u plus v dot u plus v. And when I do all of that, I'm going to get u dot u, just like I did before, plus u dot v plus v dot u plus v dot v, because I just kill off all those negative signs. It just made this a little longer, right? I'm going to get the same distribution property here. So I skipped that middle step there because you know what happens. Didn't need to write it down again. Okay, so I'm going to have the norm of u plus the norm of v. Again, both of those are squared, just like before. But then I have plus 2 copies of u dot v. So before I had minus 2 on the left-hand side. On the right-hand side, I have plus 2. Okay, so let's write our conclusion of what we have here. We have u to v is equal to u negative v. We said that's what we needed. And when I do that, I get the norm of u squared plus the norm of v squared minus 2 u dot v or v dot u, either order, is equal to the norm of u squared plus the norm of v squared plus u dot v. So we drop down, I'll have 2 u dot v is equal to a positive 2 u dot v, because I could just subtract from both sides. Okay, and I'm going to bring this over to the other side. So I'm going to have 4 copies now of u dot v. Remember, u dot v is a scalar constant. So I just like adding 7x and 7x gets you 14x. So 2x and 2x is 4x, or 2 u dot v and 2 u dot v is 4 u dot v. Then I have nothing left over here. So what this means is when I divide by 4, u dot v has to be 0. Okay, so our definition then is that 2 vectors are orthogonal okay, they're orthogonal if u dot v is equal to 0. Okay, we didn't say it here, but they're orthogonal to each other. Okay, that would be a parenthetical. It's not needed to say 2 vectors are orthogonal. When you talk about orthogonality, you are talking about the relationship between 2 vectors. So one vector cannot be orthogonal, because orthogonality has to do with the relationship between 2 different vectors. Okay, so that's what you need for 2 vectors to be orthogonal. So let's look at a couple of examples here. So if I have u is equal to 6, -1, and a vector v is equal to 4, -3, u dot v would be equal to 6 times 4 would be 24. -1 times -3 would be 3. I get 27. Okay, so u dot v does not equal 0. So u and v are not orthogonal. That means if you plot them on a graph, the relationship between them does not form a right angle. Okay, now you can imagine as you go to higher spaces, R3, R4, R17, a right angle becomes harder and harder to define or to see. Okay, so this gives us a way to quickly find, okay, is their dot product 0? They're orthogonal. If their dot product's not 0, they're not orthogonal. Okay, so like I said, we can go to higher dimensions. So I'm going to have 1, 2, -1, and 0 for u. V then is going to be 4, -2, 0, and 3. Okay, so I'm going to do u dot v. 1 times 4 is 4, minus 2 times, plus -2 times 2 is a -4, plus 0, plus 0. So I add those together, I get 0. So u and v are orthogonal. Okay, so orthogonality can be determined just by that. Is the dot product 0? If the dot product 0, the vectors are orthogonal. If the dot product is not 0, then the vectors are not orthogonal. Okay, it's that simple in terms of orthogonality. Okay, so I consider the relationship here of what it means to be orthogonal. Okay, so if I have a set of vectors, okay, we're going to call this set of vectors capital W. Okay, it's v1, v2, and v3. Okay, so W is an element of, is contained in R3. So these are three-dimensional vectors. We'll say that v1, v2, and v3 are independent. Okay, we're familiar with linear independence. So v1, v2, and v3 are in R3, and they're independent. That means they form a basis for R3. Okay. So what I want to consider is, what if I have a vector that's orthogonal to all of them? Okay. Well, if U is orthogonal to all v1, v2, and v3, that means u dot v1 is equal 0, u dot v2 is equal 0, and u dot v3 would be equal 0. Okay, so we say that that vector u then would be in the orthogonal complement. Okay, so it's all the vectors that meet this are called W, and this upside down T for perpendicular. Okay, which we also abbreviate to just W perp instead of perpendicular, because perp is easier to say. So if you're in W perp, that means you meet all these criteria. Okay, now if you think about R3 and you're going to be orthogonal to all of them, that's actually only going to happen with the 0 vector. Okay, because we're covering the whole space. I need some flexibility in order to get other vectors in that space. Okay, so there's a relationship between the column space and the null space with regard to this perpendicular situation. Okay, we're going to explore that that relationship as we continue on in the later sections. Okay, but if you're going to be orthogonal to all of those vectors, that's going to give you a very specific relationship. Okay, if I was in R4, maybe I'm going to use that fourth dimension. You know, that would be in the null space because that would be the leftover one. All right, if I only have 3 vectors, I know that I have to have 4 to be a basis. So if I have 3 in the column space, maybe only 1's in the null space. Okay, and that perpendicular nature of that is going to tell us something about the null space or tell us something about our space that we're dealing with. Okay. All right, so those are our 3 topics there for 6.1, inner product, length, and orthogonality. Okay, so in 6.2, we're going to look at orthogonal sets, okay, and some special relationships regarding projections, because we're going to use projections then to build some other definitions of sets and the like, and then have a procedure for turning a set of vectors into an orthogonal set of vectors, or an orthonormal set of vectors. So ortho for orthogonal and normal for unit vector, or normalized, or norm. Okay, so we're going to look at those as we continue in chapter 6. But that's the end of 6.1. Okay, so it's a little bit of shifting gears, but we still use those same terminologies, those same things we've been using. They still come up. We talk about independence. We talk about those relationships as well. Okay, so I'll see you in our next video for 6.2.